Imagine for a second taking your entire life savings, like every single digital asset you own.
Right. Your retirement, your whole security net.
Yeah. And just hiding all of it inside a completely mundane, everyday digital photo of your family vacation.
It sounds like a magic trick, honestly.
It really does. But I mean, a photo that you could just leave sitting right there on your computer's desktop.
Or just tossed on a random USB drive in a junk drawer.
Exactly. And anyone could look at it, they could open it, zoom in on it, and literally all they would see is a sunny day at the beach.
Completely invisible to the naked eye.
But mathematically recoverable on demand. Well, welcome to the deep dive, everyone.
Glad to be here for this one.
And I am talking directly to you, the learner out there, the one who is always, hungry to understand the hidden mechanics of this digital world we're living in.
Because today's topic is, well, it's pretty wild.
It is. Today, our mission is to unpack a truly fascinating stack of sources we've got in front of us. We are looking at comprehensive text guides, detailed system architecture screenshots, and even some raw Python code snippets.
Which is rare to see laid out so clearly.
Yeah, and all of this material is centered around this massive high-stakes problem in the Web3 and cryptocurrency ecosystem. How do you securely hide your seed phrases and private keys without relying on some third-party company?
It's a profound challenge. I mean, it is arguably the single most stressful aspect of participating in the decentralized digital economy.
Oh, absolutely.
And we are looking at a methodology today that takes advanced theoretical computer science and just distills it into an accessible, albeit unforgiving, practical tool.
Okay, let's unpack this. Because anyone who has even dipped a toe into the crypto world knows the golden rule, right?
Not your keys, not your coins.
Exactly. Not your keys, not your coins. If you do not possess the raw mathematical data that proves you own your assets on the blockchain, you don't really own them.
No, you're just asking a company for permission to access them at that point.
Right. But actually, taking self-custody, like physically storing that raw data, which is usually a 12 or 24-word seed phrase, that is an absolute nightmare for the average person.
It truly is a paradigm shift that, frankly, most people are just not prepared for.
Yeah.
Suddenly, you're acting as your own bank institution, your own security guard, and your own vault manufacturer.
That's a lot of hats to wear.
It is. And the reality is, most of us are simply not equipped with bank vault level security in our homes or, in our digital lives.
Well, looking at the sources we have, they point out the brutal reality of our standard backup methods. And I gotta say, it's kind of terrifying when you lay it all out.
It really is an eye-opener.
Okay, say you write your 24 words down on a piece of paper. Well, paper is fragile. It burns in a house fire. It degrades in a flood. Or, you just accidentally sweep it into the trash during spring cleaning.
Which happens more often than you'd think.
I bet. So then you think, okay, I'll go digital. I'll just put it on a USB flash drive.
But the sources remind us that flash memory is not permanent at all.
Wait, really? I feel like people just assume USBs last forever.
Not even close. USBs can arbitrarily corrupt. The actual microscopic electrical charges that hold your data literally bleed away and decay over a decade if the drive isn't periodically powered on.
That is wild. Just decaying in a drawer. So that leads people to make the most dangerous choice of all out of sheer convenience, right?
Oh, yeah. They open up a digital notepad on the computer they use every single day.
Yep. Saving a file called, mycryptokeys.txt or walletbackup.docx.
On a machine constantly connected to the internet.
Doing that is basically hanging a neon flashing sign for malicious actors, malware, network scrapers. I mean, it is the ultimate hacker bait.
It really is. So we are left with this immense anxiety as users.
Right. We need something better than paper, more permanent than a cheap USB, and just infinitely stealthier than a plain text file.
And that brings us right back to the scenario you posed at the top of the show.
Exactly. Hiding your net worth inside a photograph. The sources we're looking at today propose an advanced technique that merges two distinct historical disciplines of information security:
Symmetric cryptography and digital steganography.
The brilliance of this provided material is how it demystifies that merger, right?
Absolutely. We're going to look at the underlying mathematics, the biological quirks of the human eye that make it possible, and eventually the actual Python pipeline that executes it.
But to understand why this dual-layer approach is so revolutionary, we first have to understand why using either of these disciplines on their own is critically flawed.
That's the perfect starting point.
Let's start right there with the theory, because the source text makes a very clear distinction right out of the gate. It addresses a common misconception about the vulnerability of secrets and the absolute necessity of having two distinct layers of defense.
Yes, people constantly use the terms cryptography and steganography interchangeably.
Right, like they're just synonyms for hiding things.
Exactly. But the text outlines that there are fundamentally different strategies. They represent completely different paradigms of protection.
And confusing the two is a recipe for catastrophic data loss, isn't it?
Without a doubt. So, cryptography, as defined in our source guide, is security through mathematics.
Security through mathematics.
Right. The entire goal of cryptography is not to hide the existence of a message, but to take a readable message and scramble it using complex mathematical algorithms.
So it renders the data completely unreadable to anyone who doesn't have the correct decryption key.
Exactly. So it takes your seed phrase,
Yeah.
and let's use the text's simplified example here. House, car, lake, gum.
Okay, house call lake gum.
Right. It takes that and runs it through a meat grinder of math until it's just a string of absolute gibberish.
Let's briefly touch on how that scrambling actually works, because the source explicitly mentions AES, the Advanced Encryption Standard, and XOR logic.
Yeah, AES is crucial here. When you use AES, you're using what's called a block cipher.
A block cipher, meaning it chops the data up.
Exactly. It takes your data, chops it into blocks, and runs it through multiple rounds of substitution and permutation. It basically swaps bytes around, shifts entire rows of data, and mixes columns using polynomial mathematics.
Okay, so it's like shuffling a deck of cards, but doing it so thoroughly and mathematically that you'd need the lifespan of the universe to unshuffle it without the exact key.
That's a great way to put it. And at the very lowest level of this math is the XOR operation.
XOR. I've seen that acronym, but what does it actually do?
It stands for exclusive OR. It's a foundational logic gate in computer science. Basically, if you take a bit of your secret data, say a 1, and compare it to a bit of your key, say a 0 XOR outputs a 1.
Okay.
But if they are the same, like both 1s or both 0s, it outputs a 0. It's the ultimate digital toggle switch.
So when you pass your data through millions of those XOR operations governed by an AES key, the output is just, what, indistinguishable from pure chaotic noise.
Statistically indistinguishable, yes.
Yeah. Okay, so cryptography provides mathematically perfect armor. But the sources highlight a critical limitation of cryptography when used in isolation.
Yes, and this is where people get tripped up.
Right. Let's say I encrypt my seed phrase perfectly using AES. I now have a file on my desktop called, like, backup.ens.
Right.
If an adversary, a hacker who breaches my network, or a physical thief who steals my laptop spots that file, they immediately know a secret exists.
They do. They might look at it and think, I can't read this, my computer can't break this math, but I know for an absolute fact there is something highly valuable inside.
The existence of the encryption itself becomes a beacon.
Exactly. They know the secret is there, even if they can't crack the code.
I was thinking about how to visualize this for you, the listener, tying together the concepts from the text. Let me try this mental image out on you.
Go for it.
Relying solely on cryptography is basically like taking all your valuables, your gold bars, your stack of cash, your diamond rings, and locking them inside a massive, heavy, impenetrable titanium safe. And then, for some reason, you decide to bolt that safe directly to your front lawn right next to the sidewalk.
That is a phenomenal way to picture it. The math is the titanium.
Yeah.
It holds up.
Right. Everyone walking by, every neighbor, every potential thief driving through the neighborhood, they all see the safe. They all know you have something incredibly valuable in there.
Even if they can't easily open it.
Exactly. The math is good. The safe is incredibly strong. They probably can't get in with standard tools, but you have drawn a massive, undeniable target on your back.
You really have. And the adversary might try to drill it. They might try to blow it up with thermite, or, as the security industry jokes, they might resort to rubber hose cryptanalysis.
However, hose cryptanalysis, that sounds painful.
Yes, well, the weakest link in any cryptographic system is the human holding the key. If the adversary knows the safe is there, they can bypass the math entirely by just knocking on your front door with a heavy wrench and demanding the combination.
Oh, wow. Yeah. The threat is highly visible, which invites coercion.
Exactly. So that is the limitation of cryptography.
Now let's contrast that with steganography. The guide defines steganography as security through obscurity.
Right. The goal here isn't necessarily to scramble the message into gibberish. The goal is to conceal the very existence of the message.
So if an adversary is looking at your computer and they just see a generic folder full of thousands of vacation photos, they have absolutely no idea that a secret even exists.
None at all. And this taps into a long, rich history. Steganography is ancient.
The text mentions something about Greek history, right?
Yes, the word comes from Greek, meaning covered writing. Herodotus wrote about a tyrant who shaved the head of a trusted servant, tattooed a secret message on his scalp, waited for the hair to grow back, and then sent him through enemy lines.
That is wild. So the enemy searched him, found nothing, and let him pass.
Exactly. Or during World War II, spies used microscopic dots, microdots containing entire typed documents, shrunk down and glued over a period at the end of a sentence in a mundane letter.
Right. So the enemy censor reads the letter about Aunt Martha's health, sees nothing suspicious, and just passes it along. If an adversary doesn't know a secret is there, they won't even try to crack it.
Exactly.
So going back to my analogy, if cryptography is the safe on the lawn, steganography is taking your valuables, putting them in a plain, flat, brown paper envelope, and sliding that envelope under a loose floorboard in the guest bedroom.
No one knows to look for it. To the outside observer, it's just a floor.
But here is the catch, and the source material is explicitly clear about this warning. Doing just one of these things in the digital age is wildly dangerous.
Extremely dangerous.
Let's say you just use steganography. You take your plain text's seed phrase, the actual unencrypted words house, car, lake, gum, and you hide it directly into the image file.
Right, which is just sliding the plain envelope under the floorboard.
Exactly. If a motivated hacker gains access to your machine and runs a sweeping, automated steganography detection tool across every file on your hard drive, effectively stepping on every single floorboard to see if one creaks, they find the envelope.
And they open it, and boom, your money is gone instantly.
Yeah.
There is no secondary protection once the obscurity is compromised.
The obscurity is brutal.
It really is. Once broken, it offers zero resistance. What's fascinating here is how the source material insists that maximum security requires merging these two methods into a unified pipeline.
You can't rely on just the titanium safe, and you can't rely on just the hidden envelope.
No, you must combine them to neutralize the weaknesses of each. First, you lock the secret in the titanium safe, and then you camouflage the safe to look exactly like a piece of normal furniture.
That is the perfect synthesis. Let's trace the exact pipeline outlined in the text because the sequence of operations is vital here.
Let's do it. You start with your seed phrase. The very first thing that happens is it goes through that cryptographic layer.
Oh.
We use the PBKD-F2 derivation to create a key from your password, and then we use AES to encrypt the text. This turns your plaintext words into encrypted data.
Step 1 complete. The gold is in the impenetrable titanium safe.
Exactly. Now you have a highly secure but highly suspicious-looking block of binary gibberish.
Right.
Step 2. That encrypted data is then passed through an LSB steganography process. This process takes that encrypted block and weaves it invisibly into the digital fabric of an ordinary image.
And the final output is an identical PNG image.
Exactly.
Step 2 complete. The safe is now completely invisible, hidden within the pixels of the photo. If an attacker manages to suspect the photo, say they run a statistical analysis and notice an anomaly, and they somehow extract the hidden payload, they haven't won.
Not at all. All they get is that heavily encrypted gibberish. They still need your master password to crack the AES cipher.
And conversely, if an automated malware script is just scanning your computer looking for standard encrypted files or crypto-related file names to steal, it will look right past your vacation photo.
Because to the computer's operating system, it identifies purely as a standard image file. You have achieved dual-layer, zero-trust security.
It is incredibly elegant on a theoretical level, but I have to admit, when I first read this section of the source material, my brain immediately threw up a roadblock.
Oh, really?
Yeah, I had a massive point of skepticism. I'm reading this pipeline and I'm thinking, okay, I understand the concept of hiding data, but if we are literally changing the underlying digital data of an image file to forcefully stuff a cryptocurrency seed phrase inside of it, why doesn't the photo look weird?
That's the natural question, right?
Like, why doesn't it look glitchy or corrupted? Why aren't there weird neon green and hot pink pixels scattered all over my family's faces?
It is the most logical and intuitive pushback you could have. I mean, our daily experience with computers teaches us that if you alter the data of a file, you alter its output.
Yeah. If I open a Word document and change the letters in the code, the words on the screen change.
If I delete a line of code in a program, the program crashes. So why doesn't the picture change when we inject thousands of bytes of foreign data into it?
Exactly. How are we doing digital surgery on this photo without leaving a massive scar?
This brings us to the absolute core mechanics of how data vanishes into an image, a concept the source material details as least significant bit. or LSB steganography.
LSB. Okay.
To understand why the image doesn't look corrupted to the human eye, we have to zoom way, way in. We need to look past the picture itself, down to the foundational math and the pixel architecture.
Let's do it. Zoom us in to the microscopic level.
Okay, every digital image you view on a screen, whether it's on your phone, a massive 4K monitor, or an old laptop, is made up of a grid, a massive mosaic of tiny individual squares called pixels.
Right.
And in a standard full-color digital image, each one of those individual pixels generates its specific color by mixing 3 primary color channels of light: red, green, and blue. This is the universally utilized RGB color model.
It's like being back in elementary school art class, mixing primary paints, except instead of physical pigment, we are mixing digital light.
And we are mixing it with mathematical precision. Now, in the standard 24-bit image format that the text references, each of those 3 color channels inside a single pixel, the red channel, the green channel, and the blue channel, is assigned exactly 1 byte of digital storage space.
Okay, so let's break that down for the listener who might not think in bytes and bits every day. 1 byte of space. What does that mean?
1 byte is equal to 8 bits. A bit is the fundamental indivisible unit of computing. It is simply a microscopic switch that is either a 1 or a 0, on or off.
So each color channel is represented by an 8-digit sequence of ones and zeros.
Yes. Now, in binary mathematics, an 8-bit sequence can represent any integer value starting from 0 all the way up to 255.
Okay, so if I'm visualizing the single pixel, there's a digital dial for the red light that goes from 0 to 255. There's a dial for the green light from 0 to 255, and a dial for the blue light from 0 to 255.
Precisely. If the red dial is cranked all the way up to 255 and green and blue are turned completely off at 0, that pixel will shine a pure, intense, blinding red.
Makes sense.
If all 3 dials are maxed out at 255, the combined light creates pure white. If all 3 are at 0, emitting no light, you have pitch black. Every single nuanced color your screen can possibly display, millions of shades, is just a specific numerical combination of those 3 dials.
Here's where it gets really interesting. Because the source material doesn't just leave it at this abstract theory. It pulls up a specific, concrete mathematical example to prove how the steganography works without ruining the image.
It's a great example, too.
I really want to walk through this exact table from the text because this was the absolute aha moment for me.
Set up the pixel for us.
Okay, the text asks us to imagine we've zoomed into our vacation photo and we've isolated just one single pixel out of millions. And let's look solely at the red channel for that specific pixel.
Okay.
Let's say the original unmodified decimal value for that red channel is 240. That's very close to the 255 max, so it's a pretty strong, bright red.
Yes, a highly saturated red channel.
The text then shows us what the number 240 looks like in binary code, translated into those 8 bits. The binary value for 240 is 1111000, 4 ones followed by 4 zeros.
Correct. That sequence of 8 switches is the literal digital representation of that exact specific shade of red.
Now here is where the steganography engine kicks in. We need to hide our encrypted crypto seed phrase. Our secret, after passing through that AES encryption we talked about, is now just a massive chaotic stream of ones and zeros.
Right.
Let's say the very first bit of our encrypted secret payload that we need to hide is a 1. The algorithm looks at our red channel's binary. 111100000. It goes all the way to the very last bit on the far right side of that sequence.
And that final position is called the least significant bit.
Right. And currently it's a 0.
The term least significant is key here. In our base 10 number system, in the number 1492, the 2 is the least significant digit. If you change it to a 3, the overall value barely changes.
Oh, I see.
It's the same in binary. That far right bit has the smallest numerical impact on the total value of the byte.
So the algorithm takes its scalpel, rips out that original 0 at the end, and replaces it with our secret payload bit, which is a 1. The modified binary value for the red channel becomes 111100001.
Exactly.
The 7 bits on the left stayed exactly the same, only that final microscopic bit on the right changed. Now, if we translate that newly modified binary sequence back into a normal decimal number, what do we get?
The math dictates you get 241.
241. The red channel's dial changed from 240 to 241. And the text provides the full table for this theoretical pixel, applying the same logic to the other
Oh,
colors.
let's look at those.
Let's say the algorithm next needs to hide a 0 from our secret payload into the green channel. The original green value was 155, which is binary 100111011. That last bit on the right is a 1.
Right.
The algorithm violently overwrites it with our secret 0, so the sequence becomes 100111010. The green value drops down from 155 to 154.
And let's complete the pixel by looking at the blue channel in that same table. The original value is 82. In binary, that is 0101010.
Okay.
Let's say the next bit of our incoming secret payload happens to be a 0 as well. The algorithm looks at the least significant bit of the blue channel. It observes that it is already a 0.
So it doesn't need to do anything. It just leaves it alone. The blue channel stays exactly the same at 82.
Exactly. It's a perfect natural match, so no alteration is required for that specific channel.
Okay, so let's assess the aftermath. After all of that microscopic digital surgery on the binary code, our single pixel's color recipe has fundamentally shifted.
It asks.
The red dial went from 240 up to 241. The green dial went from 155 down to 154. The blue dial stayed steady at 82. And this brings us right back to my original skeptical question.
Which was?
If the color recipe has literally changed, why doesn't the image look completely messed up?
And the answer lies not in the math, but in the biological limitations of the human eye. The source material highlights this beautifully, referring to it as visual tolerance.
Visual tolerance.
Yes. You, me, the listener, the greatest art critic in the world, we physically, biologically cannot perceive the color difference between a red value of 240 and a red value of 241.
Really?
Our optic nerves and brains do not have the fidelity to register a single integer shift out of 255 possible increments.
It's an alteration so incredibly tiny that it falls entirely below the threshold of human perception. Like, if I put a massive square of pure red 240 on a 4K monitor right next to a massive square of red 241, you're saying they would look absolutely identical.
Completely indistinguishable. To our eyes, it is essentially microscopic noise. We see a seamless sky, a smooth skin tone, a solid shadow.
Well, wait, I'm going to push back on this again. Because while my eyes might be fooled, what about a machine? If I'm a sophisticated hacker, and I know this technique exists, I'm not using my eyes, I'm writing a script to analyze the image. If we are stuffing a massive crypto payload into the least significant bits, isn't that going to create a weird, detectable pattern in the file's histogram?
That is an incredibly astute observation, and it brings us back to why the dual-layer pipeline is mandatory.
Okay.
If you were hiding plain text, the actual words, house garlic gum, in the LSBs, a statistical analysis tool, like a chi-square test, would spot it immediately.
If it would.
Yes. Plain text has low entropy. It has repeating patterns, frequent letters like E and T. The statistical distribution of the LSBs would look highly unnatural.
Ah, because English isn't random.
Precisely. But remember, step one of our pipeline, we didn't embed plain text. We embedded AES encrypted data.
Right.
And as we discussed, strong cryptographic output has maximal entropy. It is statistically indistinguishable from pure, chaotic, true randomness.
Which is exactly what the natural noise of a digital camera sensor looks like at the microscopic LSB level.
Yes. The natural slight imperfections of a camera capturing light create random ones and zeros in the lowest bit layer. By encrypting the payload first, our secret data mimics that natural camera noise perfectly.
So it defeats visual inspection by humans, and it defeats statistical analysis by machines.
Exactly.
That is mind-blowing when you really start to comprehend the scale of it. A standard modern smartphone photo has, what, 12 million pixels at a minimum?
Easily. A standard 12-megapixel camera creates exactly that. And if each of those 12 million pixels has 3 distinct channels, red, green, and blue, that means you have 36 million individual color channels.
Which translates to 36 million least significant bits at your disposal, 36 million microscopic hiding spots in a single everyday photo.
It's massive.
You could hide a digital library in there, let alone a tiny 24-word seed phrase or a few kilobytes of private keys.
The capacity is staggering, which is exactly why this method is so remarkably powerful. But, and this is a massive but that the listener needs to hear clearly, that immense power comes with intense structural fragility.
Yes. Okay, I'm very glad you pivoted to that, because reading through this document right after that brilliant, elegant breakdown of the binary math, there is a section of the text that reads like a massive flashing red warning label.
It really does.
It shifts from theory to a list of absolute mandates. It's titled The Golden Rules of Steganographic Backups.
It is, without a doubt, the most critical section of the entire document. If you understand the math but fail to heed these rules, the entire system collapses.
Totally. The text essentially grabs you by the shoulders and says, okay, the math works, the concept is perfectly sound, but before you actually go and do this with your real world money, before you entrust your actual production crypto wallets to this technique, you must deeply internalize these unbendable rules.
Because if you don't, you won't just fail to hide your money, you will permanently, irreversibly destroy it.
The stakes are absolute. Let's work through them logically based on what we just learned about the pixel architecture. Knowing how fragile those microscopic LSBs are, what do you deduce the first, most terrifying threat to this entire operation would be?
Well, it has to be anything that alters the pixels.
Like,
Which brings us to rule number 1 of the text, and it's printed in all caps. Use only the PNG format.
only the PNG format. Never, ever use JPEG.
Never.
And applying what we just discussed, I can see exactly why. It comes down to how these different file formats handle image compression. The text explains that formats like JPEG utilize what is known in computer science as lossy compression.
The critical word there is lossy, meaning during the saving process, data is intentionally, purposefully lost and discarded.
Right. When you snap a photo on your phone and save it as a JPEG, the operating system's main goal isn't mathematical perfection. Its goal is efficiency.
Right, it wants to make the file size as incredibly small as possible.
Yeah, so it loads quickly on a web page, sends fast over a cellular network, or just doesn't eat up your hard drive space. To achieve that small file size, the JPEG algorithm essentially looks at the image and asks a brutal question. What tiny, imperceptible visual details can I just throw away? What mathematical data can I delete that the human eye won't even notice is gone?
And think back to our visual tolerance discussion. What are those tiny, imperceptible details? Where does the visual data matter the least?
It's the least significant bits. The algorithm specifically targets the exact location where our entire financial payload is hiding.
It is a fatal collision of intended design. The very characteristic that makes LSB steganography invisible to the human eye, the fact that altering the lowest bit doesn't matter visually, is the exact same logic the JPEG compression algorithm uses to decide what data is expendable.
Oh, man.
The JPEG algorithm uses complex mathematics, specifically discrete cosine transforms, to average out pixel blocks. It essentially comes through the image with a mathematical machete and aggressively chops off and rounds out all those carefully arranged LSBs to save space.
It's prioritizing broad visual aesthetics over microscopic data integrity, which is fatal for us. It's like painstakingly writing a microscopic life-saving message in the layer of dust on your hardwood floor and then immediately running a Roomba over it.
That's a great visual. It's gone instantly.
The compression permanently averages out the pixel values. If you take your carefully crafted steganographic image and you accidentally open it in a basic image viewer and innocently hit Save as JPEG, you have just permanently destroyed your own money. It's terrifying.
Which is why the source is so deeply adamant you must use PNG.
Because PNG is different.
Very different.
Yeah.
PNG utilizes lossless compression. It still works to compress the file to make it more manageable than raw, uncompressed bitmap data, but it does so mathematically, much in the same way a zip archive works.
Okay, so nothing is thrown away.
Exactly. When a PNG is saved and subsequently opened and displayed on your screen, it uses complex algorithms to mathematically reconstruct and preserve every single original bit exactly, precisely as it was.
In a PNG, the LSBs aren't expendable visual noise. They're treated as sacred immutable data.
Exactly. Rule 1, PNG is life. JPEG is death.
Got it.
Now, building on that understanding of how dangerous compression is, how does the guide address our modern daily habits of moving photos around?
It hits us with Rule 2, which is essentially a direct continuation of that same danger, but applied to our social lives. Rule 2, never share the image on social media or messaging apps.
This is undoubtedly where the vast majority of users would accidentally trip up and lose their assets.
Right, because you follow the pipeline. You generate this brilliant, secure PNG file. It looks like a nice picture of your golden retriever. And you think, okay, I need an off-site backup. I'll just text this photo to my mom for safekeeping, or I'll quickly drop it into my family's private WhatsApp group.
They won't know what it is, and it'll be safe in the chat history.
Exactly. But the source guide specifically lists the major culprits here: WhatsApp, Telegram, Facebook, and Instagram.
You have to consider the business models of those companies. All of these platforms are built to move massive, staggering amounts of media across the internet instantly, billions of times a day.
Exactly. The text uses a phrase that I absolutely love. It states that these platforms violently compress uploaded media.
Violently compressed.
Because they have to. They are trying to save millions of dollars in server storage and network bandwidth costs. When you take your pristine, mathematically perfect, lossless PNG and upload it to a WhatsApp chat, WhatsApp's servers immediately intercept it.
Right.
The server code essentially looks at it and says, this file is too large and inefficient. We are going to aggressively optimize and transcode this before we route it to the recipient's phone.
And that back-end optimization process instantly strips out the hidden data.
Poof, gone.
The platform converts your PNG into a highly compressed JPEG or WebP format, resizes the dimensions, and repixelates the entire grid. The image that eventually arrives on your mother's phone might still visually look like your golden retriever, but your seed phrase is entirely irrevocably gone.
The steganographic payload is essentially sanitized out of existence by the platform's ruthless infrastructure.
It is an invisible, silent hazard. You look at your phone, you see the sent message, the picture is right there on the screen, and you go to sleep thinking your financial backup is perfectly safe in the cloud.
But it's an empty shell, a ghost.
It's exactly.
So the source mandate is very clear. You must treat the steganographic image file with extreme paranoid operational security. You store the original, completely untouched PNG file on physical media. Offline USB drives hidden in a safe. External solid-state drives stored at a secondary physical location.
And what about the cloud? Because the guide does mention secure cloud storage, but it includes a highly specific, critical caveat.
Right. It says you can use the cloud, but the image must be inside an encrypted .zip archive.
That's crucial.
You don't just drag and drop the raw PNG to Google Drive, Dropbox, or iCloud. If you do, those cloud providers often run their own background image preview generators or thumbnail creation tools that could inadvertently alter the file metadata or the pixels themselves.
Yes.
Instead, you put the PNG inside a standard .zip file, you put a password on that .zip file, and you upload the archive.
The logic there is sound. To the cloud provider servers, a zip file is just an opaque block of generic binary data. They don't know it's an image, so their image compression algorithms ignore it.
It creates a robust, protective digital wrapper around the image to ensure the bits remain completely undisturbed in transit across the internet and at rest on their servers.
Okay, that brings us to Rule 3. And this one is stated with absolute sobering gravity in the text. Rule 3. Do not forget your password.
It seems like such an obvious statement in the digital age, but the implications here are profound.
If we connect this back to the bigger picture of what we are actually building, we have to realize that this entire system relies on the cold, unfeeling mathematical robustness of the cryptographic algorithms involved.
Yeah, the source doesn't sugarcoat it. It says there is absolutely no backdoor. Zero.
None. There is no forgot password link to click. There is no customer service representative you can email a copy of your driver's license to in order to prove your identity and regain access.
It's just you and the math.
The cryptographic layer, that first step where we put the seed phrase into the titanium AES safe, is designed by the brightest mathematical minds and cryptographers on the planet to be utterly impenetrable. If you lose the specific decryption password you chose, the math doesn't care that it's your life savings locked inside.
The math doesn't care that you're stressed or that it was an honest mistake.
The heavy vault door swings shut, locks, and the key is instantly thrown into a black hole.
The steganography aspect might work perfectly. You might diligently preserve the PNG on a secure offline drive for decades. You might successfully extract the encrypted binary payload from the LSBs.
But without that master password, you just have a massive string of mathematically perfect, unsolvable gibberish.
You will stare at the encrypted data, knowing your wealth is right there, but you will never, ever be able to read it. The seed phrase is gone forever.
It really forces a mindset shift.
Yeah.
It forces you to take profound personal responsibility for your own security architecture. You are building a vault, you are the architect, and you are the only one on Earth with the combination.
Okay, so we've exhaustively covered the theory. We deeply understand the cryptography locking up the data, the LSB steganography camouflaging the lockbox within the microscopic color channels, and the golden rules of PNG formats and offline storage.
We have the foundation.
Now, we are going to bridge the gap. We've talked about the perfect crime, the invisible safe, but how does an average person actually pull this off without a PhD in applied cryptography?
That's where the tools come in.
Right. The sources gave us an actual Python environment to do it. Let's look at the engine they built.
This is where the source material transitions from abstract theory to immensely practical application, providing actual visual evidence and code snippets of the tool in action.
Yes, the sources include a detailed series of screenshots taken from a Jupyter Notebook. It is essentially a step-by-step visual and technical guide to the exact pipeline we just spent the last half hour discussing.
It's a great walkthrough.
I want to act as our navigator here and walk you, the listener, through exactly what these screenshots reveal to see how you would actually perform this operation on your own machine. Let's explore the environment setup and the core Python libraries.
To set the stage properly, the source document notes that this tool is explicitly designed to run within a Jupyter Notebook environment.
For those listening who might not be software engineers, what exactly is a Jupyter Notebook?
It's an incredibly powerful, interactive digital document. It allows you to seamlessly combine live, executable programming code, explanatory formatted text, and interactive visual user interfaces, all running harmoniously right inside your standard web browser.
And the text points out that this flexibility is key. You can run this notebook locally on your own computer if you have Python installed, or you can run it on cloud platforms like Google Colab or other standard data science environments.
But looking at the very first screenshot provided, it gives us a crucial, highly specific detail about the environment being used in this demonstration.
Yes, that initial setup is revealing.
Let's break it down.
The first image is a small dialog box titled Select Kernel. The drop-down menu shows that the user is actively selecting Python 3.13 xPython to execute a file named steganography.crypto.ipynb. There is also a small checkbox checked at the bottom that says Always start the preferred kernel.
This tells us immediately that the foundation of this tool is a very modern, bleeding-edge Python 3.13 environment.
Why does that matter?
This ensures the latest security libraries, the most efficient execution speeds, and the newest cryptographic standards are available to the code. The specific xPython backend reference often indicates a specialized environment optimized for secure, isolated, browser-based execution.
But I'm going to inject some skepticism here, representing the average crypto user. This all sounds incredibly secure, but you're asking a normal person who just wants to protect their Bitcoin to boot up a Python environment, navigate a Jupyter Notebook, manage dependencies, and run code blocks.
That's a lot to ask.
Isn't that high level of user friction going to lead to massive, catastrophic mistakes?
That is a highly valid concern. The command line is an intimidating place for most people, and typos in cryptography can be disastrous.
Exactly.
However, the subsequent screenshots address that exact friction directly. Let's look at the first code block executed, step 1. It's titled Install Required Libraries. We see a specific command executed, pip install pillanumpy ipwidgets, and underneath we see the output logs of the installation process.
Let's break down exactly why these three specific libraries are the absolute bedrock of this tool and how they solve that user friction problem.
Okay, let's start with the first one, Pillow. The text briefly notes this handles standard image loading and saving.
Right. When you point a Python program to a photograph on your hard drive, the core Python language itself doesn't inherently know how to decode the complex header data of a JPEG or encode the compression algorithms of a PNG.
Pillow is the necessary bridge. It is a massive, robust library that reads the file format, decodes it into a raw matrix of pixel data that Python can understand, and crucially, when we are done modifying those microscopic LSBs, Pillow is responsible for correctly, mathematically, packaging that data back into a perfect, lossless PNG file.
It is the file handler that ensures rule number 1 is strictly followed.
Okay, the next library is NumPy, and the text gives a very dense description here. It says NumPy allows for high-speed, vector-based manipulation of pixel matrices.
That sounds like high-level data science jargon.
It is, but its application here is absolutely vital for usability. Think back to our discussion about the scale of the image. A standard photo has 12 million pixels, equating to 36 million individual color channels.
Right.
If you ask standard native Python code to look at channel 1, change the bit, move to channel 2, change the bit, and do that sequentially one by one in a simple for loop, it would be agonizingly, unusably slow. It might take several minutes or even longer just to encode a single image.
Right, and if there's one thing users hate more than the command line, it's sitting there staring at a frozen loading bar for 10 minutes, wondering if the program crashed and destroyed their seed phrase.
Exactly. NumPy completely changes the game. It doesn't use standard Python loops. It treats the entire image as a massive mathematical matrix, a single unified data structure. It then performs operations on thousands or millions of pixels simultaneously by utilizing highly optimized, low-level C code running under the hood.
And this process is called vectorization.
Yes, vectorization. It turns a pixel-by-pixel operation that would take minutes into a massive, sweeping matrix operation that takes fractions of a second. It is the high-performance engine that makes the steganography instantaneous.
That makes total sense. Speed is a feature. And the third library is AP Widgets. The guide states this builds the visual user interface right in the notebook cells. And I imagine this is the direct answer to my concern about user friction.
Spot on. Without IP widgets, you would have to interact with this powerful engine via long, complex command line arguments. You have to type something like Python steganography.py -- input photo.jpg and so on.
Yeah, that's awful.
It is prone to typos, syntax errors, and is deeply intimidating. IP widgets allows the notebook to dynamically generate actual clickable buttons, secure text boxes, and native file upload dialogues right there in the browser window.
Oh, that's nice.
It takes this advanced academic cryptographic engine and wraps it in an interface accessible to anyone who knows how to click a mouse and type in a web form.
And looking closely at the installation output logs in that screenshot, we see some incredibly interesting, highly technical details. It states that the packages are 100% WASM compatible. It references a tool called Mamba.js 0.19.13. And it notes that the requirements for Pillow, NumPy, and IP widgets were already handled by condo/micromamba/mamba.
That is perhaps the most crucial security detail in the entire document. WASM stands for WebAssembly.
Mm.
Decades ago, web browsers were just simple document viewers. Then JavaScript made them interactive. But WASM is a revolution.
How so?
It essentially turns your web browser into a full-blown, high-performance virtual machine capable of running compiled languages like C, Rust, or in this case, a full Python environment securely inside a sandbox.
And why does that matter for our seed phrase?
Because it means that this entire complex Python environment, including the heavy cryptographic hashing, the AKS encryption, and the massive NumPy matrix manipulation, is capable of running entirely 100% locally inside the user's web browser memory.
Oh.
The Mamba.js reference confirms this fast browser-based package management. At no point is your C phrase, your password, or your image ever transmitted across the internet to a remote server for processing. It's a massive security feature. It creates an isolated, zero-trust enclave on your machine.
The secret literally never leaves your laptop. That is brilliant architecture. Okay, moving along the pipeline. We have another screenshot of a code cell that shows some back-end functions being defined. The most visually prominent one is a Python function called createDownloadLink.
Yes, this function handles the very final step of the encoding process. After the Pillow library is finished saving the newly modified secret-filled PNG into the virtual environment's memory, this function creates the mechanism for the user to securely retrieve it and save it to their actual hard drive.
Yeah, analyzing the code in the screenshot, it's quite clever. It takes a variable called data, which represents the raw image bytes. It imports a library called base64 and specifically utilizes the b64 encode function.
Right.
It mathematically converts those raw binary image bytes into a long text string, and then it embeds that string directly into a constructed HTML anchor tag. It even has specific CSS styling written right into the Python code. I see background #4CAF50, which is a specific modern shade of green, and padding.12p by 24px to make the button large and clickable.
It's generating a nice, clean, highly visible download button directly in the notebook's output cell, avoiding any complex file system navigation for the user.
And at the bottom of the screenshot, we see the output log confirm, a green check mark, and core functions loaded successfully. But while that specific screenshot shows the UI code, the text guide elaborates heavily on the invisible cryptographic heavy lifting happening silently in this step.
Yes. The back-end security logic. We touched on it earlier, but the text names the exact specific algorithm being loaded here. PBK DF2-HMAC HA2566.
Which, to a beginner, looks like a terrifying, randomly generated string of letters and numbers.
Let's demystify every piece of that acronym, because understanding this is crucial to trusting the vault. We know AES is the titanium safe, but AES requires a key of exactly 256 bits.
Right.
When you type in your master password, let's say it's something long but memorable, like my first car was a Blue Honda 1998, that password is not actually used to encrypt the data directly.
It's not.
No. Human-created passwords, even strong ones, have relatively low mathematical entropy. They are too predictable for raw encryption algorithms like AES to use directly as a key.
Right. Humans are inherently bad at generating truly random, chaotic strings of characters. We rely on words and patterns.
Exactly. So PBKDF2, which stands for Password-Based Key Derivation Function 2, acts as a mathematical translator.
Okay, that makes sense.
It takes your human-readable password and runs it through a one-way cryptographic hashing algorithm to generate a completely random, mathematically perfect, high-entropy cryptographic key of the exact right length for AES.
And the specific hashing algorithm it uses is SHA-256, which is the exact same cryptographic hash function that secures the entire Bitcoin network.
Correct. SHA-256 takes any input and produces a unique, fixed-size 256-bit hash. It relies on the avalanche effect. If you change even one single letter in your password, the resulting hash changes completely and unpredictably.
But the text notes two very specific additions to this PBKDF2 process that make it even more robust. It explicitly states it uses 10,000 hashing iterations and a unique random 16-byte salt.
These are the critical defenses against modern brute force attacks. Let's start with the iterations.
Okay.
Setting the PBKDF2 algorithm to 10,000 iterations means it doesn't just scramble your password through SHA-256 once. It takes the password, hashes it, takes that chaotic output, and feeds it back into the hash function again and again and again, exactly 10,000 times.
Why intentionally force the computer to do that much extra math?
To purposefully slow down the processing speed, to you, the legitimate user, running 10,000 iterations on a modern CPU takes maybe a tenth of a second. You click the button, you blink, and it's done. You don't even notice the delay. But to an attacker who has stolen your image and is trying to guess your password by running millions of guesses a second using an automated offline dictionary attack, that tiny delay is devastating. Multiplied by millions of guesses, it makes the attack computationally unfeasible. It would burn too much electricity and take thousands of years to be worth the effort.
That is incredibly clever design. It's like putting a massive, heavy vault door on an intentional, mandatory timer delay. And what about the unique random 16-byte salt? What does that protect against?
A salt is a string of purely random data generated by the computer and secretly appended to your password before the hashing process even begins. This thwarts something called the rainbow table attack.
A rainbow table.
Yeah, highly footed attackers sometimes use supercomputers to pre-compute the SHA-256 hashes for every single common password in the dictionary, and they store those results in massive databases called rainbow tables. If they steal your hash, they just look it up in their table, and if it matches, they know your password instantly without having to do the math.
Oh, wow. But if a random, unique 16-byte salt is secretly mixed in with your password before the hashing starts, the final hash will be completely, uniquely transformed, rendering all of their massive, pre-computed rainbow tables entirely useless.
Exactly. And the final piece of the acronym is HMAC, Hash-Based Message Authentication Code. This is a crucial integrity check. When the data is encrypted, the HMAC is generated. Later, when you try to decrypt it, the HMAC proves that the ciphertext hasn't been tampered with.
So it's an integrity check.
Right. If even a single bit of your steganography flips, say cosmic radiation hits your SSD and changes a 1 to a 0 in the LSB, the HMAC verification will fail instantly. The program will warn you that the data is corrupted rather than silently spitting out a subtly incorrect seed phrase that would lose you your funds.
So even before the data is mapped to the RGB channels for the steganography, the cryptographic vault it is placed inside is layered with multiple state-of-the-art interlocking defenses: iterations, salting, HMAC integrity, and AES encryption.
The foundation is mathematically rock solid.
Okay, now for the part where it all comes together. The UI walkthrough. We have detailed screenshots of Step 3A, which handles the encoding, and Step 4A, which handles the decoding. Let's start with 3A. I'm looking at the visual interface dynamically built by those IP widgets we discussed.
Walk us through the specific user experience. What does the interface ask of them?
It's remarkably clean and intuitive, completely avoiding the complexity of the math underneath. At the very top, there's a button with a standard upload icon that reads, Upload Image. The user in the screenshot has clearly already clicked this because directly below it in the live processing logs, it displays Processing Image, Photo 2026 Zoo2 27 08.20.44.jpg.
A standard raw smartphone photo file name, complete with date and timestamps.
Right. Then there's an incredibly useful diagnostic readout. Image capacity, 462,236 bytes. This is brilliant UI design. The program calculates exactly how much hidden data the image can comfortably hold before you even start typing.
It does that by scanning the image dimensions, calculating total pixels, and determining exactly how many viable LSBs are available across the RGB channels.
Exactly. Below that capacity readout is a large multi-line text area, clearly labeled with a little padlock icon, secret text. And inside that text box, the user has typed their sensitive seed phrase. In this specific visual example, it's shortened to just 4 words for demonstration: house, car, lake, gum.
A shortened example, but perfectly illustrative of the process.
The UI provides immediate real-time feedback. Below the text box, a small label dynamically updates to say, your text size, 18 bytes. So as a user, I instantly know I need to hide 18 bytes of data, and my image has over 460,000 bytes of capacity. I have plenty of room.
The ocean is vast. Your drop of water is incredibly small.
Next is a standard password text field labeled with a golden key icon, password. It's filled with those little black dots concealing a 12-character password. Finally, there is a prominent, unmissable green button at the bottom, hide secret in image. The user clicks it, the live logs immediately update, encrypting and hiding data.
And in those few seconds, that entire pipeline executes. The PBKDF2 hashing runs 10,000 times, the salt is generated, the AES block cipher scrambles the text, the HMSC is calculated, Pillow converts the JPEG to an uncompressed matrix, NumPy vectorizes the data and mathematically surgically replaces the LSBs across the RGB channels, and Pillow prepares the final file format, all happening locally and visibly in the browser memory.
And then the log updates with a green check mark. Success! Your secret has been hidden. And directly below that, generated by that specific base64 code we analyzed earlier, a massive green button appears with a little download tray icon. Download secretimage.png. You click that button, and the browser saves the newly created secure asset locally to your standard downloads folder. You now possess the camouflaged vault.
It is an incredibly streamlined workflow. You have successfully merged high-level cryptography and microscopic steganography without touching a single line of command line code or understanding the underlying vector mathematics. But of course, a backup system is entirely useless if you cannot reliably restore it. Let's look at the recovery process.
Right. Step 4A. Extract your hidden data. The user has lost their hardware wallet, they need their money back, and they are in a high-stress situation. They load up the Jupyter Notebook on a secure, offline computer. Now, there is a highly specific mechanical step of the text notes here, accompanied by a small, zoomed-in screenshot. You don't use the widget upload button for recovery right away. First, you must navigate to the File Browser tab of the Jupyter interface itself.
Yes. The screenshot highlights the top navigation menu bar of the Jupyter environment. File, Edit, View, Run, Kernel. Below that is the standard file navigation directory tree.
And there's a specific icon highlighted with a red square in the screenshot. It's a small button with an arrow pointing up from a tray. The hover text, captured perfectly in the image snippet, reads, Upload files.
This preparatory step ensures the target PNG image is securely uploaded directly into the local file system of the isolated Jupyter virtual environment before the extraction script runs, maintaining that zero-trust local execution.
So the user clicks that and uploads their secure PNG. In the Step 4A screenshot, we see the UI for extraction. It's even simpler than encoding. Just a drop-down Upload PNG button to select the file they just brought into the environment, and a single password field.
The user selects the file named secretimage.pnea from the dropdown.
They carefully type in their 12-character master password, and they click a large teal button labeled Extract Secret.
And the program instantly shifts into reverse. It uses Pillow to read the perfect, lossless PNG. It uses NumPy to sweep across the matrix and extract all the microscopic LSBs. It isolates the encrypted binary payload. It takes your password, runs the PBKDF2 derivation with the salt to rebuild the AES key. It checks the HMAC to ensure the image hasn't been corrupted. It uses the AES key to decrypt the payload. And if every single mathematical check clears,
the live logs show processing, extracting, and decrypting data, and then a beautiful green checkmark appears. Success! Your secret has been recovered. And sitting right there on the screen, framed by equals signs for visibility, is the plain text. House, car, lake, gum. Your seed phrase is instantly revealed in a private, offline environment.
it really synthesizes everything perfectly. What we are seeing here is the practical, executable implementation of a true zero-trust architecture. You are not trusting a cloud provider's servers. You are not trusting a web server application. You aren't even trusting your operating system's normal, potentially compromised file viewer.
Everything happens locally.
Every single operation happens locally, governed entirely by immutable mathematics, executing right there in your browser or local offline notebook.
It's deeply empowering. In a digital world where we are constantly handing our data over to massive corporations, this tool lets you take total sovereign control of your own security architecture. So as we step back and look at this entire massive stack of sources, let's summarize the core takeaways for you, the listener. By combining the unyielding mathematics of AES cryptography and the microscopic obscurity of LSB steganography, you create a backup mechanism that is virtually invisible to both human eyes and machine analysis.
It protects you from casual, physical observers who might snoop on your computer, and it protects you from sophisticated, automated network scrapers hunting for plaintext files.
And the rules are the uncompromising guardrails that make the magic work. By strictly, fanatically using lossless PNG files, fiercely avoiding the violent compression algorithms of social media and messaging platforms, and maintaining rigorous, disciplined offline storage habits, you can confidently hide incredibly sensitive, life-altering data-like API credentials, cold wallet seed phrases, or raw private keys behind the facade of a completely mundane, everyday digital photo.
That's the core of it.
So, what does this all mean? We have explored this incredible tool. We deeply understand the binary math. We've seen the Python code execute perfectly. I'm going to hand it over to you for a final thought based on all of this material. When we zoom out from the code and look at the human element, what is the ultimate takeaway here?
It raises an incredibly important, almost philosophical question, a tension that is inherent in the very nature of perfect steganography. We've spent this entire, extensive deep dive admiring the creation of the perfect invisible lockbox. But steganography's greatest, most celebrated strength, its sheer undetectable invisibility, might also be its greatest fatal flaw over a long enough timeline. Think about it realistically. You follow all the golden rules perfectly, you run the Python code, you hide your massive life savings perfectly in a single, beautiful family vacation photo. You save it flawlessly as a PNG. You store it on an offline encrypted hard drive in a safe. And then, decades pass. Life happens. You might pass away unexpectedly. How do your heirs, your spouse, your loved ones know which specific photo out of the 100,000 photos on your backup hard drives contains the family fortune?
Wow. If it's truly invisible to an automated machine, it's invisible to them too.
Yeah, exactly. If an advanced state-sponsored adversary cannot detect it using statistical analysis, neither can your grieving children. They might just look at a massive folder of old digital JPEGs and PNGs, think, oh, these are nice memories, but taking up too much space, and casually format the drive to reuse it. The profound tension here is between ultimate security against malicious theft and ultimate loss due to pure, tragic obscurity. When you build a lockbox so mathematically perfect that it truly vanishes from reality, you take on the immense, stressful burden of ensuring it can never be found again by the right people. It is a deeply human problem that the math cannot solve, and it is something every single user must deeply mull over and plan for before deploying this architecture in the real world.
That is a chilling but absolutely necessary reality check to end on. Security doesn't exist in a vacuum. It exists across time and across generations. Thank you to everyone out there for joining us on this extensive deep dive. Keep exploring these complex concepts, stay skeptical and curious about the digital tools you use, always respect the unforgiving power of cryptography, and for the love of everything, always remember to save as PNG. You don't want to accidentally compress your own wealth out of existence just because it looked like a mundane photo. Until next time.